in Chapter 9. We're going to look at simulations, we're going to look at odds, and then expected values. So a simulation would be a technique that's used to act out a problem by conducting the experiments. Think about crash testing. When they are crash testing cars, they are testing the behavior of the car in a crash situation, so it's a simulation. Using simulations, we can typically estimate a probability using mini trials rather than just use theoretical probability, which we know isn't perfect. There's something called a random digits table. So the digits in this table form a list of digits selected at random by a computer or a calculator. So this is a sample one that you can utilize. To simulate a coin toss, you're going to pick a number at random to start and then read across the table, letting even digits represent heads and odd digits represent tails. Because there's a 50-50 chance, that's why we're given even to certain numbers and tails to other numbers. So how would this work in an actual problem? A baseball player has a batting average of 0.4 or 40%. That is, his probability of getting a hit on any particular pitch that's thrown at the bat is 40%. If I want to estimate the probability he'll get at least one hit in his next 3 times at bat, I can use a random digit table with a hit represented by 0, 1, 2, and 3, because I need to have 4 out of the 10 digits. So I'm looking at how many numbers in this random number table have the digits 0, 1, 2, and 3. So that would be 42 out of the 50 trials. So the estimate for the probability is 42 over 50. So the 4 digits came from 40%, which would be 4 out of 10. So that's why I have 10 digits, and when I go 0 to 9, so 4 numbers out of that would create it, and that's how I would know. So there's pretty good odds of getting a hit. Now, suppose Corey makes enough for 100 chocolate chip cookies and then mixes 100 chocolate chips into the batch. So if the chips are distributed at random, so that means like we're not spacing them out, and he chooses a cookie at random from the 100 cookies he makes, I want to estimate the probability that has exactly 1 chocolate chip. So I would create the 10 by 10 grid to represent the 100 cookies he made. Each cookie can be associated with some ordered pair where the first component is the horizontal and the next is the vertical scale. So I can use tally marks to then divide up those chocolate chips, and I would see there are 34 out of 100 ways by counting the squares that have exactly 1 tally. Now, if I want to compute odds, odds are slightly different from probability, and a lot of times they're confused and there's like an overlap that's seen there. So if I want to look at the probability that event A occurs, and then I would let P of the complement of A, remember the line at the top means complement, be the probability that it does not occur. Then if I'm looking at the odds in favor of an event, odds are actually calculated by the probability that it happens divided by the probability that it does not happen, okay? So the odds against an event would be the complement divided by the probability. So you have to first figure out, are you looking at the odds in favor of, or are you looking at the odds against an event? Then you're going to calculate them using the number of favorable outcomes over unfavorable outcomes. That's how we're going to get that odd figure to show up. So if I'm looking at the odds in favor of an event occurring of rolling a number less than 5, that would be 4 to 2 or 2 to 1. Why? Because if I want odds in favor, going back to that formula, I want to look at the number of favorable outcomes divided by unfavorable outcomes. So rolling a number less than 5 on a die, well, there's 1, 2, 3, 4. There's 4 digits that are less than 5. And then if I want the unfavorable outcomes, that would be greater. So I would have 5 and 6. So that would be 2, which would be 2 to 1 when I reduce it. If I want to toss heads on a fair coin, there is one way to toss heads. There is one way to toss tails, so it's a 1 to 1. Here I'm looking at drawing an ace from an ordinary 52 card deck. Well, there's 4 aces, that's my favorable outcome, and there's 48 cards in the deck. So there's 48 other ways not to get an ace, or a 1 to 12. Drawing a heart from the card deck, there are 13 hearts, so that's my favorable outcome. Then not getting a heart would be 52 minus that 13, which would be 39, which reduces to 1 over 3. When we're reducing those odds, it's the same thing as reducing a fraction. So you're going to reduce it the same way you would reduce 13 divided by 39. So if I want to actually start computing odds, then I can start looking at this formula. for for and against, where I have the odds of an event happening are m, then I have this other value n. So if I do an expected value, which is a slightly different concept, this is just visualizing what we've already seen. If I start looking at expected value, this is going to involve multiple probabilities that are happening. Expected value is going to be an expectation of what we would see based on probabilities that we've calculated. So it can be used to predict the average result in an experiment if we're doing it a lot of times. It cannot be used to determine the outcome of a single experiment. It has to use multiple ones. So a lot of times we use this with fair games, because a fair game would be when the payoff and net winnings are zero, so that the expected value minus the cost to play the game breaks even, and we call it a fair game. So here's an example of one of those types of problems. Suppose you pay $5 to play the following game. Two coins are tossed, you get $10 if two heads occur, $5 if one head occurs, and nothing if you don't get any heads. Is this a fair game? So when I'm looking at this, I've got to find the probability of getting two heads, which is 1/4. The probability of getting one heads would be 1/2, and the probability of getting no heads would be 1 out of 4. My expected value will be to take that probability and multiply it by each possible winning amount. So if I get two heads, I get $10. If I get one heads, I get $5. So I take the probability of one head times $5. If I get no heads, that's going to be 0. So if I get my expected value out here, I get $5 as my expected value. So I pay in $5 to play the game. My expected winning is $5. 5 minus 5 is 0. So this is a fair game.